In the second training session on Geneon NAC, we will discuss the components that make up the NAC system. This is the table of contents for Chapter 2 educational content. First, product components. Second, product-to-product communication. Third, the composition plan for the policy server and network sensor. Let's proceed in order. In this chapter, we will introduce the components that make up Geneon NAC and explain the functionality of each component. Geneon NAC is composed of the following three components. 1. Policy server establishes and manages policies. 2. Network sensor performs access control and collects network information. 3. Agent installed on user devices to collect information and control the interface. Let me explain the detailed functions of each component. Policy server manages policies, network sensors, and agents. It also stores collected real-time information. Additionally, it provides a log management function to store and search system-wide audit logs and supports AIAA, authentication, authorization, accounting, for external authentication. Network sensor performs role-based network control according to policies and detects abnormal traffic. Agent installed on user endpoints to collect information and verify endpoint integrity. The policy server consists of 4 key components. 1. Web server collects information and performs policy management. 2. Database server, which stores collected information and stores changed information. 3. Log server, which stores real-time logs in the system and policies. 4. Radius server provides authentication, authorization, and accounting functionality. The network sensor consists of 2 key components. 1. There is a web server for managing the files, but it cannot be configured if it is a network sensor without a disk. 2. Enforce controls access based on the role of the endpoint device. The agent consists of 3 components. It is categorized based on the supported operating systems, Windows, Linux, and macOS. It is installed on endpoints to perform information collection and integrity verification. On the policy server, daemons operate based on its 4 components. 1. Web server. To perform policy management and act as the web console, the following daemons are executed: Centered, Tomcat, Apache, and GDCID. 2. Database server. The MySQL daemon, a relational database, is used. 3. Log server runs on Tomcat and utilizes the Elasticsearch daemon as a dedicated search engine. 4. Radius server. The Radius daemon, based on open-source software, is used. Additionally, common daemons such as SSHD for secure shell access, SensorD, and Procmon for monitoring are also executed. On the network sensor, daemons operate based on 2 components. Web server. The Apache daemon runs to handle file management and distribution. Enforcer. The GDCID daemon operates for redirecting to block pages related to enforcement. Additionally, common daemons such as SSHD, SensorD, and Procmon are also executed. To enable file management and distribution, you need to configure the proxy service for OS update feature on network sensors equipped with hard disks. The Geneon NAC system architecture is divided into 3 parts. The foundation is built on the Linux kernel and Java. Custom-developed software based on C and C++. Software provided as open source on the Linux platform. The following is a network diagram showing the positions of each NAC component when deployed in a network. The policy server is typically placed in a secure environment, such as a server farm or DMZ, where it is better protected compared to other networks. The network sensor can be configured in multi or single setups across the entire network. The agent is installed on user endpoints. The following is a network diagram showing the use of network sensors in both single and multi-configurations. As shown in the diagram, for smaller networks, such as remote offices, a single configuration is used. For larger networks, like headquarters, where multiple VLANs are utilized, multi-sensor configurations are deployed using trunk port settings on the switches. The following is a network diagram showing the use of network sensors in multi-sensor and mirror sensor configurations. As shown in the diagram, for smaller networks such as remote offices, instead of deploying a network sensor, a mirror sensor can be configured in the L3 segment. For larger networks, like headquarters, where multiple VLANs are used, multi-sensor configurations are deployed using trunk port settings on the switches. First, Genion NAC is composed of three components: policy server, network sensor, and agent. Among these, the agent is optional components depending on the environment. Second, each component is further divided into detailed subcomponents as follows. The policy server is divided into web server, database server, log server, and radius server. The network sensor consists of web server and enforcer. The agent is categorized based on supported operating systems: Windows, Linux, and macOS. In this chapter, we will explain the port information and its purpose used for communication in NAC. Let me explain the overall network communication between the NAC components. The policy server requires network communication with the network sensor, agent, and external data servers. Additionally, the network sensor requires communication back to the policy server. The agent also needs to communicate with both the policy server and the network sensor. The reason for defining network communication for each component is to ensure that if systems like firewalls or packet management tools exist in these communication paths, the appropriate exceptions can be configured. The policy server communicates with the Genion update server using TCP 443 and TCP 80 ports. This communication is used for Genion data updates and message transmission. Additionally, it periodically synchronizes server time with the NTP server using TCP 37. The network sensor and agent use UDP 3871 to transmit events or check their operational status through Keep Alive packets. The network sensor communicates with the policy server using TCP 443 and TCP 80 for policy reception and file downloads. It uses UDP 3870 to send Keep Alive packets for operational status updates and UDP 514 to transmit logs generated on the network sensor to the policy server. The agent communicates with the policy server using TCP 443 for policy reception. It uses UDP 3870 to send Keep Alive packets for operational status updates. If the network sensor does not have a file management feature, the agent requests file transfers directly from the policy server using TCP 80. If the network sensor has a file management feature, the agent requests deployment files and patches from the network sensor using TCP 80 and TCP 8080. First, the policy server must communicate over the network to receive services provided by Genions. Second, for Keep Alive communication to verify operational status, it uses UDP 3871 and UDP 3870 ports. In this chapter, we will explain the configuration methods for Genion NAC, focusing separately on the policy server and the network sensor. The NAC policy server can consist of 3 components, each of which can be itemized. The first is a single configuration, where all modules are configured to work on one machine. While there are cost advantages, the disadvantage is that it takes a long time to recover from a failure. The second is the multiple configuration, in which the modules are configured to operate separately depending on the situation. While there are advantages in terms of performance, the downside is that it takes the same time to recover from a failure as a single configuration. The third HA configuration, the redundant configuration, is divided into redundancy in a single configuration and redundancy in a separate configuration. HA in a single configuration can compensate for the shortcomings in terms of shortening the time to recovery from a single configuration failure. But it is not recommended for large sites because it has no performance advantage. Next, there is redundancy in the multiple configuration. As above, the time reduction from the time of failure to recovery and the performance of the multiple configuration. But there is an issue related to cost, because it is necessary to purchase up to 8 policy servers. The configuration to be set this time will proceed with a single configuration that all modules are set up on one device as shown below. A single configuration has the advantage of cost savings, but it has the disadvantage of having a single point of failure that can prevent the entire service from failing in the event of a single module failure. In the multiple configuration of the policy server, one or more modules run across multiple devices. This setup offers the advantage of improved performance compared to the single configuration. However, it still has a single point of failure. If any one module fails, the entire service may be disrupted. In the HA configuration of the policy server, all modules are separated and run on individual devices. This setup offers 2 key advantages: improved performance compared to other configurations. Even if one module fails, the system can continue to operate without impacting the overall service, thanks to its fault-tolerant design. The NAC network sensor can be configured in 5 different ways. Let me explain each method. 1. Single configuration. In this setup, the network sensor is configured using its physical interfaces only. As mentioned in Chapter 1, depending on the network sensor model, the number of physical interfaces can range from 2 to 8. Each interface can be assigned to one network, meaning the number of interfaces determines how many networks can be managed. 2. Multi-configuration. In the multi-configuration, the network sensor creates multiple logical interfaces through VLANs. While VLANs can be logically created up to 250, it's recommended to configure no more than 64 VLAN interfaces per network sensor for optimal performance. 3. HA configuration. The HA configuration ensures high availability of the network sensor. This setup addresses the issue of service interruptions caused by network sensor failures, allowing continuous operation even when a failure occurs. 4. Mirror configuration. In the mirror configuration, the network segment managed by the network sensor is moved to layer 3, allowing IP-based network control. For this setup, the switch must support mirroring functionality. However, there are limitations. The sensor cannot control or collect information from networks below the monitored layer 3 segment. 5. Bonding configuration. In the bonding configuration, multiple physical interfaces of the network sensor are combined into a single virtual interface. This setup supports high availability and bandwidth expansion for switches connected to the network sensor. The single configuration of the network sensor uses as many physical interfaces as the number of network segments to be managed. This method is used when the number of managed network segments is less than or equal to the available interfaces on the network sensor. It is typically applied when there are available switch ports or when deploying the network sensor in a single network. The multi-configuration of the network sensor involves setting up a trunk interface for VLAN-based networks to create logical network sensors. In this method, up to 255 VLANs can be logically configured and managed through a single physical interface. This approach is used when the number of networks to manage exceeds the available physical interfaces on the network sensor. It is recommended to configure a maximum of 64 VLANs per network sensor for optimal performance. The HA configuration of the network sensor uses the VRRP to ensure high availability. In this setup, VRRP assigns a virtual IP to configure HA. This allows the system to address issues related to continuous service availability caused by network sensor failures. The mirror configuration of the network sensor utilizes the mirroring feature of switches to control IP communication. While a standard network sensor operates on a Layer 2 basis, the mirror configuration is used when Layer 3 based control is required. This setup has the advantage of cost reduction because fewer network sensors are needed compared to a standard Layer 2 environment. However, it comes with a limitation. Communication in networks below the monitored Layer 3 segment cannot be controlled. Additionally, it may be necessary to calculate the mirrored packet volume and implement load balancing through a Layer 4 switch to manage traffic effectively. The bonding configuration of the network sensor is designed to handle switch failures connected to the network sensor. Bonding offers 7 modes, each providing specific capabilities for fault tolerance or bandwidth expansion, depending on the mode selected. Typically, it is used to address single points of failure in switches by combining multiple physical interfaces into a single bonded interface for high availability. First, the policy server can be configured in 3 options. Second, the network sensor offers 5 configuration options depending on the environment and requirements. In this time, we learned about the components that make up Geneon NAC, network communication between components, and the configuration of the policy server and network sensor. In the next time, we will learn how to configure Geneon NAC configuration.